what if the universe, your thoughts, your body, the stars, the void between them, was a fleeting sketch on a cosmic canvas, poised to be erased? What if reality, in all its vast and ancient splendor, rested on a delicate, invisible thread, a thread that could snap without warning? In the eerie, probabilistic realm of quantum mechanics, this is not mere fantasy. It is a chilling and profound possibility. Our universe may exist in what physicists call a false vacuum, a fragile, temporary state of being, teetering on the edge of a catastrophic collapse, a single, random quantum flicker, at any moment, in any corner of the cosmos, could unleash a wave of absolute transformation, a bubble of a new, more fundamental reality expanding at the speed of light. There would be no explosion, no sound, no final, dramatic flare. Just an instant, silent, and irreversible transition. Atoms would unravel. The laws of physics would be rewritten. Time and space as we know them would dissolve into an unrecognizable form. You would not feel it. You would not see it. Your existence, along with everything you have ever known, loved, or dreamed of, would simply be no more. This is not science fiction. It is a possibility rooted in the strange and beautiful logic of quantum tunneling. A world where the impossible becomes probable over the vast, lonely expanse of cosmic time. This is a descent into science's deepest and most unsettling uncertainty, a journey to the very foundation of existence, a journey that could redefine everything. You wake up to a normal day. The familiar light of the sun filters through your window. The sky is a placid, reassuring blue. The quiet routines of life unfold with their comforting predictability. But far away, in a distant, anonymous corner of the cosmos, reality begins to fail. A silent, unstoppable ripple of change begins to spread, and end with no warning, no sound. Just a wave of absolute nothingness. Or rather, a wave of a new something that renders our something obsolete. This is not the plot of a dystopian novel. It is the core of the false vacuum hypothesis. The idea that our universe, in all its seeming permanence, hides a fragile cosmic lie. Every theory of physics, from the elegant curved space-time of Einstein's equations to the bizarre, probabilistic truths of quantum mechanics, is held together by a set of fundamental assumptions, a trust that the universe is, at its core, stable. We trust space and time to behave consistently. We rely on the fundamental particles, the electrons, the quarks, the photons, to act the same way today as they did yesterday, and as they will tomorrow. But what happens if reality itself decides to shift? What happens if the very foundation of existence, the vacuum state that underpins all physical laws, begins to dissolve? In the deep, cold silence of interstellar space, we now know that the void is not empty. The quantum fields that constitute the most basic level of reality tremble with a latent, potent energy. Invisible. Virtual particles blink in and out of existence, a constant, ghostly dance that hints at a deeper, more chaotic reality, simmering just beneath the ordered surface of the world we perceive. The event horizons of black holes, those one-way membranes at the edge of space-time, whisper secrets about the nature of information and entropy. Secrets we can't yet fully decode. Secrets that might one day burst forth and rewrite the very architecture of existence. The boundary between what we know and what we think we know is becoming razor thin, and in the light of our newest and most powerful instruments, we are starting to see the cracks. The James Webb Space Telescope, our golden eye on the infant cosmos, is peering further back in time than anything that has come before it, and it is revealing galaxies in the early universe that are too mature, too structured, too complex to fit our established cosmological models. They are behaving in ways that challenge every theory we have ever built about how the universe should have evolved. Our quantum computers, the first generation of machines that can harness the strange logic of the quantum realm. Running trillions of calculations a second, sometimes produce answers that seem to defy classical logic, giving us glimpses of a computational reality that is far richer and more complex than our own. Are we simply glimpsing a deeper, more subtle structure of reality? Or is the structure itself beginning to glitch? The universe, we must remember, does not owe us consistency. It has never promised to behave in a way that fits neatly into our theories. And if the very fabric of space-time is not woven from the familiar threads of particles and strings, but from something even stranger, something more fundamental if consciousness, or information, or entropy lies at the very core of it all, then pulling on what we think is a loose thread could unravel the entire tapestry. This is the profound and unsettling moment in which we find ourselves, as a species, as a civilization of curious minds. We are not just standing at a new frontier of physics. We are standing at the precipice of a reality that may no longer be stable. Every new breakthrough, every new theory, peels back another layer of the cosmic onion. But what if, one more layer down, we find not a deeper truth, but a final, catastrophic collapse? This idea of a cosmic cliff is not just a theoretical abstraction. It is a possibility so wild, so fundamentally unnerving, that even the most brilliant and courageous minds in science hesitate to speak its name too loudly. It is the idea that our reality might not just be misunderstood, it might be on the very verge of breaking. And if that cliff gives way, there is no telling what is waiting for us in the vast, silent, and utterly alien void that lies beyond. When we hear the word vacuum, our minds conjure images of emptiness, of a space devoid of all matter, a silent, static void where nothing happens. But in the strange and beautiful world of quantum physics, a vacuum is anything but empty. It is a seething, vibrant, and incredibly energetic medium, pulsing with ghost-like particles, with virtual interactions, and with the raw, untamed potential for all of existence at every single point in the universe, from the heart of a star to the darkest, coldest corner between the galaxies. Space is never truly still. It is alive with an invisible, incessant motion. And this fundamental reality is far stranger, and perhaps far more dangerous than anyone in the classical world ever imagined. To understand this, we must first step into the world of quantum fields. This is not just an abstract mathematical idea. It is the most fundamental description of reality that we currently have. In this picture, everything we perceive as a particle, the electrons in our atoms, the photons of light that strike our eyes, the quarks that make up the protons and neutrons in our nuclei, is not a solid, point-like object in the traditional sense. It is a ripple, a vibration, a temporary, localized excitation in a deeper, more fundamental field that fills all of space. Imagine a vast, calm ocean stretching to infinity. This ocean is the field. Now, imagine a single wave rising from its surface. That wave is the particle. Every type of particle in the universe is associated with its own unique field. An electron is not a tiny object flying through space. It is a disturbance in the electron field. A photon is a ripple in the electromagnetic field. And the infamous Higgs boson, the particle that gives other particles their mass, is just a brief, fleeting swell in the omnipresent Higgs field. The vacuum, then, is simply the state we get when all of these fields are in their lowest possible energy state. their ground state. It is the state where no particles are being actively excited. But crucially, this does not mean that the fields are gone or that they are calm. They are still there, at every point in space, and they are still foaming, flickering, and jittering with a baseline level of quantum uncertainty. This is where things start to get unsettling, because for decades, physicists have harbored a deep and troubling suspicion that our vacuum, the one in which our entire universe is embedded, might not be the true vacuum. It might be a false vacuum. That term, though technical, is chilling in its implications. It means that the vacuum state we live in, the foundation of our reality, is stable for now, but not truly stable. It is metastable. It is like a pencil balanced perfectly on its sharp tip. It could stay that way for 1 billion years, or it could fall over in the next second. The idea arises from the mathematics of quantum field theory itself. The energy landscape of the universe is not necessarily a simple single valley. There can be multiple potential configurations for how the quantum fields can arrange themselves, some with lower energy than others, like a series of valleys of different depths in a vast, mountainous terrain. Right now, all the fields in our universe might be sitting together in a shallow valley, a local minimum in this energy landscape, thinking they have found their most comfortable, lowest energy state. But what if, hidden beyond a high and wide energetic barrier, there lies a deeper valley, a true vacuum, a state of even lower energy, a more fundamental and more stable version of reality? If our universe were to somehow transition into that deeper valley, a process that is allowed by the strange laws of quantum tunneling, it would trigger a cataclysmic event known as vacuum decay. A tiny microscopic bubble of this true vacuum would spontaneously appear somewhere, anywhere, in space, and it would instantly begin to expand at the speed of light. Inside this bubble, the laws of physics as we know them would cease to exist. The fundamental constants of nature would change. The forces that govern the universe would warp and transform. The very particles that make up atoms, the protons, the neutrons, the electrons, might become unstable or cease to exist altogether. Chemistry would stop. Biology would be impossible. Matter itself could dissolve into a soup of unfamiliar, exotic components. This is not a fiery, cinematic explosion. There is no shockwave, no mushroom cloud. It is far more insidious and far more final. It is a silent, light-speed wave of metaphysical erasure. The bubble of the new reality would not just destroy our universe, it would overwrite it, replacing it with a new and utterly alien set of physical laws. This is not a far-fetched fantasy. The mathematics of our best, most well-tested theory of particle physics, the Standard Model, not only allows for this possibility, but, depending on the precise values of certain fundamental constants, may even suggest it. When physicists at the Large Hadron Collider discovered the Higgs boson in 2012, the world celebrated it was the final missing piece of the Standard Model puzzle. But as the champagne flowed, a more sober and unsettling realization began to dawn. The measured mass of the Higgs boson, about 125 giga-electron volts, was a number that seemed strangely and precariously perched. When this value is plugged into the complex equations that describe how the fundamental constants of nature change at very high energies, it suggests that our universe may indeed be in a metastable, false vacuum state. It is like nature itself is whispering to us, a faint, disquieting murmur from the depths of the quantum void. You are not supposed to be here. What keeps us safe, for now, is the immense energetic barrier that separates our current vacuum from the potential true vacuum. Quantum tunneling, the process by which the universe could make this leap, is an incredibly rare and improbable event, especially over large distances and high energy barriers. But improbable is not the same as impossible. It just takes one single, random quantum fluctuation, one fortunate quantum twitch in the right place, to tip the cosmic balance, or worse. It could be triggered by an external event, a moment of extreme energy density, like the collision of two super heavy cosmic rays, or, as some have worried, the impact of a future, even more powerful particle accelerator that could provide the nudge needed to push us over the edge. This is why the term fragile balance is not just a poetic exaggeration. It is a literal physical description of the foundation of our universe. Everything we do, every scientific experiment we conduct, every single second that we exist, relies on a kind of cosmic faith, a trust in the permanence of a vacuum state that may, in fact, be temporary. And what is even more fascinating is that this same delicate vacuum structure may be intimately tied to our own cosmic origins. The period of rapid inflationary expansion that is thought to have occurred in the first moments after the Big Bang is believed to have been driven by the energy of a high-energy false vacuum state. When that state decayed, it released the energy that created all the matter, all the stars, all the galaxies we see today. In other words, a form of vacuum decay may be what created everything, what it giveth. It could also taketh away. And the story takes another, even stranger, twist. Some physicists, working on the frontiers of cosmology and string theory, now believe that other regions of the cosmos, other bubble universes in a vast multiverse, might already exist in that true vacuum state. They would be alternate pockets of reality, sealed off from us by their own different laws of physics, completely unreachable and utterly alien. We would not even know if one of these bubbles of true vacuum was expanding towards us until the very moment it arrived, rewriting our existence in its silent, light-speed wake. The vacuum is not empty. It is the deepest and most potent kind of fullness, a fullness that is charged with rules, with forces, with hidden truths, and it is not guaranteed to last. We are walking on a thin, shimmering film of cosmic surface tension, blissfully unaware of the deep, dark, and potentially more stable ocean that lies just beneath. One fluctuation, one transition, and it could all change. And if that change comes, we will not see it coming. There will be no warning, no alarm, no final, heroic stand, just the silent, instantaneous birth of a new and alien universe, and the sudden, complete, and utterly silent erasure of our own. There is something profoundly and existentially unsettling about the notion that the universe could simply disappear, not with a bang, but with a silent, instantaneous whimper. No dramatic buildup, no cosmic countdown, no final, poignant moment to make peace with the end, just existence, in all its richness and complexity, wiped clean, overwritten in an instant. This is not the plot of a nihilistic science fiction movie. It is a real physical possibility that is baked into the elegant and often terrifying equations of quantum field theory. At the heart of this ultimate nightmare scenario is a process so calm, so quiet, and yet so utterly final that it almost defies our comprehension. It is called vacuum decay, and the agent of this cosmic apocalypse is a bubble. A bubble so small at its inception, so blindingly fast in its expansion, and so fundamentally destructive in its nature, that if it ever forms, it will be the very last thing the universe ever knows. To understand how this bubble could end everything, we must once again revisit the concept of the false vacuum. Imagine a vast, rolling landscape of hills and valleys, where the altitude represents the energy level of the universe's quantum fields. Our universe, in its current state, may be like a marble sitting comfortably in a small, shallow dimple on the side of one of these hills. It is in a local minimum of the energy landscape. It is stable enough to stay put, to give the illusion of permanence. But if there is a deeper, wider valley nearby, a global minimum or true vacuum, then the marble is not truly, fundamentally stable. It is in a state of metastability. And in the strange, probabilistic world of quantum mechanics, systems are not strictly bound by the limits of classical energy. Thanks to the bizarre and wonderful phenomenon of quantum tunneling, a particle, or indeed an entire field, can spontaneously and randomly tunnel through an energy barrier that it classically should not be able to overcome. It is as though the marble, without any push or any warning, simply disappears from its shallow valley and instantly rematerializes in the deeper one. In the context of the cosmos, this means that the vacuum of our universe itself could suddenly and spontaneously decay. One moment, space is as we know it. The next, a tiny, microscopic bubble of the lower energy. True vacuum could pop into existence, anywhere, at any time. This bubble would not be an empty void. It would be a region of a new and more fundamental kind of reality. And it would be surrounded by a thin spherical wall, a domain wall, which is a phase transition front where the old false vacuum is being converted into the new true vacuum. Inside this bubble, the very laws of physics would be rewritten. The fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces would behave differently. The fundamental constants, like the speed of light or the charge of the electron, might shift to new values. The particles that make up our world, the quarks, the leptons, the Higgs boson might become unstable, or they might not even be able to exist at all. The very rules of chemistry and biology would be rendered null and void. The intricate, delicate dance of atoms that allows for the existence of stars, of planets, of life, would be impossible. Matter itself, in all its forms, could simply dissolve into a soup of unfamiliar, exotic components, or perhaps just a bath of pure, undifferentiated energy. The process of destruction is not an explosion in the cinematic sense. There is no fiery shockwave, no expanding cloud of debris. It is far more subtle and far more absolute. The bubble of true vacuum expands outwards in all directions at the speed of light. This is a fundamental and unavoidable speed limit. It means that nothing can outrun it. No signal, no particle, no warning can escape from its expanding edge to alert distant observers. There is no place to hide, no force that can resist it. You would not see it coming because the bubble would reach you at the very same instant as the first photons of light from its expanding wall. The erasure would be instantaneous and total. Theoretically, this catastrophic transition would begin in an infinitesimal region of space, a region far smaller than a single subatomic particle. But due to the immense energy released in the transition from the false vacuum to the true vacuum, this tiny bubble would begin to expand at a relativistic speed. Within a fraction of a second, it would balloon outwards, converting everything in its path into the new, alien reality of the true vacuum. From its random point of origin, it would stretch across solar systems, across galaxies, across the vast, empty voids of intergalactic space, devouring stars, planets, dark matter, and even the fabric of space-time itself. It would not just kill the universe, it would overwrite it, replacing our familiar, life-bearing cosmos with a new, and likely sterile, one. What is perhaps most chilling about this scenario is that it is not just a wild, hypothetical possibility. It is a feature that is allowed, and in some models even suggested, by our best and most well-tested theory of particle physics, the Standard Model. As we have seen, when physicists use our current measured values for the masses of the Higgs boson and the top quark to calculate the stability of our universe's vacuum, they find that we seem to be living in a state of metastability. We are not clearly in the safe, stable zone, but are perched uncomfortably close to the tipping point. According to the most recent calculations, our vacuum is likely stable enough to last for many billions, or even trillions, of years. But this is a probabilistic statement, not a guarantee. The timescale for such a decay is unimaginably long, but it is not infinite. And it is based on the assumption that there are no other, as yet undiscovered, particles or forces that could affect the calculation. But this is not a comfort, because quantum tunneling does not require a push. It does not care about time or place. It can happen spontaneously, at any moment, governed only by the cold, impartial laws of probability. The longer the universe exists, the more chances it has to roll the dice. The more likely it is that this ultimate, cosmic snake eyes will eventually occur. It is like playing a game of Russian roulette with the cosmos. A game where the gun has a near infinite number of chambers, but the bullet is real, and every single tick of the universal clock is another pull of the trigger. Inside the bubble of true vacuum, the nature of reality would be completely alien. Physicists speculate that it would not be an empty nothingness, but would be a universe structured according to a different set of physical laws. The fundamental particles might be different. The forces might have different strengths. The very dimensionality of space and time could be altered. It would be, in every sense of the word, a new universe, a universe that had obliterated the old one to make room for its own. Strange existence. And yet there is a deep and almost poetic irony to this idea. The very same mechanism of vacuum decay that could one day end our universe may also be the mechanism that created it in the first place. The period of cosmic inflation that is thought to have kick-started the Big Bang was driven by the decay of a high-energy, false vacuum state. So, vacuum bubbles are not just destroyers, they are also creators. They are the engines of cosmic change, rewriting reality, both ending and beginning worlds in the same, silent, light-speed breath. And it is even possible, in the context of a larger multiverse, that our universe is just one bubble among many, a temporary, metastable island in a vast, chaotic sea of other, and perhaps more stable, vacuum states. In this picture, countless other bubble universes may already exist, each with its own rules, its own time, its own matter, its own minds. Perhaps, somewhere in the deep, cosmic void, another bubble of true vacuum is expanding right now, its silent, invisible wall headed our way. Perhaps its edge will pass through us in 1 trillion years, or 1 billion years, or tomorrow. But this is not a horror story meant to induce a sense of cosmic dread. It is a story about humility. The universe does not operate according to our human-scale expectations of permanence and stability. We may never fully understand the deep architecture of the quantum vacuum, nor predict when or how it might shift. But we can, and we should, appreciate the sheer, improbable strangeness of existing at all, of being a conscious, questioning being, balanced on a thin, delicate thread of temporary physics, wrapped in a set of beautiful, but perhaps fleeting, laws. For now, the bubble has not formed. The vacuum holds. And reality, in all its fragile, flickering, and utterly miraculous glory, continues. When scientists at the Large Hadron Collider at CERN announced the discovery of the Higgs boson in 2012, the moment was met with a wave of global celebration. It was a triumph of human ingenuity, the culmination of a decades-long, multi-billion-dollar quest to find the final, missing cornerstone of the standard model of particle physics. The Higgs was the key. The particle predicted nearly half a century earlier that was responsible for imbuing other fundamental particles with their mass. But behind the champagne and the applause, as physicists began to pore over the data and to calculate the precise properties of their newly found quarry, an unsettling whisper began to emerge from the heart of the universe itself. A whisper that grew louder and more insistent as the numbers were crunched. Because buried in the measured mass of the Higgs boson was a potential and deeply troubling warning sign that reality as we know it, the very fabric of our existence, may be far more fragile than anyone had ever dared to hope. To understand the Higgs field and its troubling implications, we must first grasp its profound and central role in the cosmos. In the strange and beautiful world of quantum field theory, every fundamental particle is associated with a field that permeates all of space. The Higgs field is unique among these. It is not responsible for a particular force, like the electromagnetic field, or for a particular type of matter, like the electron field. Its job is far more fundamental. It is responsible for giving mass to the other fundamental particles. In the first, fiery moments after the Big Bang, the universe was an incredibly hot and energetic place. In this state, all the fundamental particles were massless, zipping around at the speed of light in a wild, chaotic, and unstructured dance. Then, as the universe expanded and cooled, it underwent a profound phase transition, much like water freezing into ice. The Higgs field, which had previously been turned off, suddenly turned on, settling into a non-zero value throughout all of space. It was as if the entire cosmos was suddenly filled with an invisible, molasses-like energy sea. And as the other fundamental particles moved through this sea, they began to interact with it, to drag against it. This interaction is what we perceive as mass. Some particles, like the Do and Z bosons that carry the weak nuclear force, interact very strongly with the Higgs field, and so they are very heavy. Other particles, like the electron, interact more weakly, and so they have a smaller mass. And some particles, like the photon, do not interact with the Higgs field at all, and so they remain massless, forever traveling at the speed of light. This cosmic phase transition, the turning on of the Higgs field, was a pivotal moment in the history of the universe. It was the first, crucial brushstroke of structure in a previously featureless cosmos. Mass allowed particles to slow down, to clump together under the influence of gravity, and to eventually form the stable, complex structures of atoms, of stars, of planets, and of life. Without the Higgs field, the universe would be a cold, dark, and featureless soup of massless particles, and we would not be here to wonder about it. In this sense, the Higgs field is not just a scientific curiosity. It is a fundamental pillar of our reality. But here is where the story takes its strange and unsettling turn. When physicists measured the mass of the Higgs boson, the particle associated with the Higgs field, they found it to be about 125 billion electron volts. And when they plugged this number, along with the measured mass of the top quark, into the complex equations of the Standard Model, they could begin to map out the potential energy landscape of the Higgs field itself. And what they found was deeply concerning. In a perfectly stable universe, one would expect the mass of the Higgs to correspond to a vacuum state that is at the very bottom of the energy landscape. A true vacuum where the field is resting comfortably and permanently in its lowest possible energy state. Instead, the measured values of the Higgs and top quark masses seem to place our universe in a state of metastability. It is as if the Higgs field is not sitting at the bottom of the deepest valley in the energy landscape, but is perched precariously in a shallow, local valley, with a much deeper and more stable valley lurking just beyond a high energy barrier. Our universe is like a thin sheet of ice stretched across a deep, cold lake. It is holding for now, but a sudden, violent fluctuation, a quantum nudge, could cause the Higgs field to tunnel through the barrier and to cascade down into that lower, more stable energy state. This is the process of vacuum decay, and the consequences would be absolute. A bubble of this new, true vacuum would form and expand at the speed of light, rewriting the laws of physics as it went. The very existence of stable atoms, of chemistry, of life, is a property of our current, metastable vacuum. In the true vacuum, these structures would be impossible. Our reality would be erased. The reason the measured mass of the Higgs is so concerning is not just the value itself, but its relationship to the other fundamental constants of nature. Physicists use a set of powerful mathematical tools called renormalization group equations to project how the values of these constants change at very high energies, like the energies that were present in the early universe. And when they plug in the known masses of the Higgs boson and the top quark, they find something chilling. The calculations suggest that the Higgs potential, the energy of the Higgs field, may actually dip below zero at extremely high energies. This would create a true vacuum well that is far, far deeper than our current state, implying that while our universe feels stable, it might just be temporarily perched on a high and precarious energy plateau. In practical human terms, this suggests that we are living in a universe that is balanced on a cosmic knife's edge. Any significant disturbance, any extreme fluctuation, any rare, high-energy event could, in principle, push the Higgs field over the edge and into that deeper, true vacuum state. And once that process starts, the shift would be unstoppable. A bubble of the new vacuum would expand at the speed of light, its wall of pure energy obliterating all existing structures in its path. The fact that we have not yet observed such a cataclysmic event suggests two equally profound possibilities. The first is that our universe is, in fact, more stable than our current calculations suggest. Perhaps there is new physics beyond the standard model, new particles, new forces, new symmetries like supersymmetry that kicks in at very high energies and stabilizes the Higgs potential, flattening out the dangerous dip. The search for this new physics is one of the primary motivations for building ever more powerful particle accelerators, like the future upgrades to the LHC. The second possibility is more disturbing. It is that we simply have not waited long enough. The timescale for a spontaneous quantum tunneling event to trigger a vacuum decay in our universe is, according to most calculations, unimaginably long, many billions or even trillions of years, far longer than the current age of the universe. This is comforting on the surface, but it is a statistical comfort, not a guarantee. And it is based on the assumption that nothing comes along to give the universe a push. Could a high-energy particle collision, like the ones we create at the LHC, be that push? This was a question that sparked a brief but intense global debate around the time the LHC was first turned on. The consensus among physicists is a firm no. The cosmic rays that are constantly bombarding the Earth's atmosphere from deep space are smashing particles together with energies that are far, far higher than anything we can achieve in our terrestrial accelerators. And this has been happening for billions of years. If vacuum decay could be triggered that easily, it almost certainly would have happened already. The universe itself is a far more powerful particle accelerator than anything we could ever build. But the delicate, fine-tuned nature of our universe's stability remains a deep and profound mystery. What is striking is how close to the edge we seem to be, a slightly heavier Higgs boson. Say at 130 GeV instead of 125 would have placed us safely and comfortably in the realm of a perfectly stable vacuum. A slightly lighter one could have made the universe catastrophically unstable from the very start. The fact that our measured value is hovering right on the very precipice, right on the dividing line between these two fates, has led many to wonder whether this is just a random coincidence or a clue to some deeper truth. Could this be evidence for a multiverse in some versions of string theory? The landscape of possible universes contains a vast number of different vacuum states, each with its own different set of physical constants. In this view, we simply live in one of the rare bubble universes where the Higgs field happened to settle into a metastable, but very long-lived, state. Other bubbles might be more stable, or they might have already decayed. Our universe is habitable not in spite of its potential instability, but perhaps because of it. The Higgs field, then, is both a great gift and a terrible gamble. It is the cosmic field that gives us mass, that gives us structure, that gives us the very fabric of our visible universe. But it is also a field that sits atop a deep and dark abyss of a truer, more fundamental reality, an abyss into which our entire cosmos could one day plunge. The measured mass of the Higgs boson does not just explain why things are the way they are. It also reminds us that they did not have to be this way, and that they may not stay this way forever. It pulls back the curtain on a universe that is far more delicate, more mysterious, and more profoundly dynamic than we ever imagined. And in doing so, it leaves us with the most haunting and most human. Of all questions, how long does our reality have left? In the familiar classical world of our everyday experience, certainty reigns. A ball rolls downhill. A glass shatters when it is dropped. An object stays where you put it, unless an external force acts upon it. This is the world of Newton, a world of predictable, deterministic laws, a world that makes intuitive sense to our evolved, macroscopic brains. But at the deepest, most fundamental level of reality, at the subatomic scale, all bets are off. Welcome to the quantum realm, a world where particles can pass through solid walls, where probabilities trump certainties, and where the laws of physics seem to resemble a strange and wonderful game of cosmic dice rather than a neatly written, deterministic rulebook. And at the very heart of this strangeness, at the core of this quantum weirdness, lies a phenomenon that feels like pure, unadulterated magic: quantum tunneling. Imagine a single particle, an electron, trapped inside a box with thick, high walls. In the classical world, if the electron does not have enough energy to climb over the walls of the box, it is stuck inside forever. The walls are an absolute, impenetrable barrier. But in the quantum world, that same electron has a small, but non-zero, chance of simply vanishing from one side of the wall and reappearing a moment later on the other side, without ever having had enough energy to go over the top. It is as if reality itself has glitched for a moment, as if the particle has found a secret, hidden passageway through an impossible obstacle. This is quantum tunneling, and while it may sound like something from the pages of a science fiction novel, it is one of the most well-tested and well-established phenomena in all of quantum mechanics. Tunneling is not a rare or niche event. It is a cornerstone of the quantum world, a process that is happening constantly, all around us and even within us. The very sun that warms our planet shines because of quantum tunneling. In the incredibly hot and dense core of the sun, hydrogen nuclei are being fused together to form helium, releasing a tremendous amount of energy in the process. But the temperature and pressure in the sun's core are not quite high enough for these nuclei, which are all positively charged and therefore repel each other, to get close enough to fuse in the way that classical physics would demand. It is only because of the probabilistic magic of quantum tunneling that these nuclei can occasionally overcome their electrostatic repulsion and get close enough for the powerful or short-range strong nuclear force to take over and bind them together. Without quantum tunneling, the sun would not shine, and life on Earth would not exist. Quantum tunneling is also at the heart of many of our most advanced technologies. The transistors in the microchips that power our computers and smartphones rely on electrons tunneling through thin, insulating barriers. The flash memory that stores our data works by trapping and releasing electrons in a floating gate, a process that is only possible because of quantum tunneling. And the scanning tunneling microscope, a device that allows us to see individual atoms on a surface, works by measuring the tiny quantum tunneling current that flows between a sharp metal tip and the surface it is scanning. The rules that govern quantum tunneling emerge directly from the wave-like nature of particles in quantum mechanics. A quantum particle, as we have seen, is not a solid, point-like dot. It is better described by a wave function, a mathematical expression that represents a cloud of probability, a range of possibilities for where the particle might be found. And this probability wave does not stop abruptly at an energy barrier. It decays exponentially into the barrier. If the barrier is thin enough, the wave function can have a small but non-zero amplitude on the other side. This means that there is a finite, calculable probability that the particle, when a measurement is made, will actually be found on the far side of the barrier. It is not that the particle has climbed the barrier or drilled a hole through it. It is that its existence, its reality, was always, in a probabilistic sense, smeared out over both sides of the barrier, and the measurement simply revealed it to be on the other side. Now, let us take this strange and powerful idea and apply it not just to a single particle, but to the very fabric of the universe itself. Imagine that our entire universe, with its specific set of physical laws and its particular vacuum energy state, is like that particle trapped in a box. It is sitting in a false vacuum, an energy state that appears to be stable, but is not the true, lowest energy configuration possible. And there is an energy barrier that separates our current state from a potential, lower energy, true vacuum state. In this scenario, our entire universe is a quantum system, and like any quantum system, it is subject to the laws of quantum tunneling. Even if it does not have enough energy to classically climb over the barrier and transition to this lower energy state, there is a finite, non-zero probability that it could, at any moment, simply tunnel through. This is the terrifying and beautiful logic of vacuum decay. It does not need a cause, a trigger, a push. It just needs time. And in a universe that is billions of years old and that may exist for trillions more, the improbable can become the inevitable. The longer the universe exists, the more chances it has to roll the quantum dice. The more likely it is that a vacuum decay event, a bubble of true vacuum, will spontaneously appear. It is not a cosmic error, not an external force, not a sign of a fundamental instability. It is simply the universe obeying the strange, deep, and inexorable logic of its own quantum nature. The spontaneity of quantum tunneling is what makes the prospect of vacuum decay so profoundly unsettling. There is no way to predict it, no way to prepare for it. Every point in space is a potential launch site for this ultimate cosmic phase transition. And once it happens, the bubble of the new true vacuum will expand outwards at the speed of light, its wall of pure energy rewriting the laws of physics as it goes. Nothing can stop it. Nothing can outrun it. You would not even see it coming. The inevitability of quantum tunneling, when applied to the cosmos as a whole, makes our universe feel less like a permanent, solid home and more like a temporary, and perhaps even accidental, arrangement of physical law. The longer our universe exists, the higher the statistical odds become that it will, eventually, make the quantum leap to a new, and likely very different, state of being. It is as if reality itself is playing a game of cosmic Russian roulette, a game with an almost infinite number of empty chambers, but one that is being played over an almost infinite amount of time. The bullet of vacuum decay is, in a statistical sense, guaranteed to fire eventually. The only question is when, and that is the ultimate cosmic mystery. It could be in 1 billion years, or in 10 trillion years, or it could have started 1 billion years ago, on the far side of the observable universe, its silent, light-speed wave of destruction already on its way. The thought is both sobering and, in a strange way, awe-inspiring. Quantum tunneling is not a force of pure, random chaos. It is a process of predictable randomness. We can, in principle, calculate the probabilities. We can chart the potential decay rates. We can simulate the dynamics of the bubble's expansion. But we can never, even in principle, pinpoint the exact time or location of the event. It is like living next to a volcano that has no seismograph, no warning signs. You know that it will, one day, erupt. You just do not know when. And this deep quantum unpredictability is not just a feature of our future. It may also be the key to our past. Some physicists, as we have seen, argue that the Big Bang itself, the very origin of our universe, may have been a quantum tunneling event, a spontaneous transition from a prior, perhaps timeless, vacuum state. A sudden, probabilistic snap from one energy level to another, igniting the explosive expansion that birthed all of space and time. If that is true, then quantum tunneling did not just shape our potential future. It created our entire past. It is the alpha and the omega of our cosmic story. And so, for all its terrifying and destructive power, for all its potential to erase our entire reality, quantum tunneling is also a profoundly creative and deeply humbling principle. It is a reminder that we live in a universe that is not a static, finished product, but a dynamic, evolving, and endlessly surprising process. It tells us that nothing is guaranteed, nothing is permanent, not even the vacuum of space that we take for granted. Every moment that we exist, we do so on borrowed time, a gift of statistical fortune. Our continued survival is not something that is owed to us by the cosmos. It is something that is granted, moment by moment, by the strange and beautiful laws of chance. Quantum tunneling transforms the universe from a solid, reliable stage into a cosmic casino, a place where the dice are always rolling, and the stakes are absolute. And whether we like it or not, we are all players in this grand, mysterious, and ultimately unpredictable game. If the strange and beautiful logic of quantum tunneling threatens the very existence of our own single universe, the natural and even more unsettling question is, where does it end? What if the cataclysmic fallout of a vacuum decay does not stop at the boundaries of our own cosmic bubble? What if the collapse of one universe is just the first silent tremor in a much larger and far more interconnected cosmic landscape? What if it is like knocking over the first domino in an infinite, trans-dimensional line of realities? This is not just the stuff of comic books or speculative science fiction. It is a genuine, if highly speculative, idea that arises from a serious consideration of the physics of the multiverse. It is the idea that the entire multiverse itself could be vulnerable to the same existential quantum glitch. To even begin to understand this possibility, we must first stretch our imagination far beyond the confines of our own familiar cosmos. The idea of a multiverse proposes that our universe is just one of many, perhaps even an infinite number, of other universes, each with its own unique set of physical laws, fundamental constants, and vacuum states. Some of these other universes might look a lot like ours. Others could be radically and unimaginably different, with different numbers of dimensions, different particles, different forces. This idea emerges naturally from several of our most ambitious physical theories, from the many worlds interpretation of quantum mechanics to the theory of eternal cosmic inflation. In this vast cosmic archipelago, our universe is just one island, now. Here is the unsettling part. If one of these island universes, any one of them, undergoes a vacuum decay, what happens next if the laws of quantum field theory allow one universe's false vacuum to collapse into a lower energy, true vacuum, forming an expanding bubble of a new reality? Could that bubble, in theory, interact with its neighboring parallel universes? And could that interaction be a catastrophic one? In a multiverse that is governed by a single, overarching energy landscape, all the different bubble universes can be thought of as sitting in different valleys of this landscape. Some are in deep, stable valleys. Others, like perhaps our own, are in shallow, precarious, metastable ones. If one of these universes collapses to a deeper, more stable valley, the resulting true vacuum bubble might not respect the fragile, interuniversal boundaries. It could, in principle, breach the thin, higher-dimensional membranes or branes that are thought to separate the different bubble universes, causing a chain reaction, a cosmic avalanche of vacuum decay, a multiversal domino effect. This may sound like pure fantasy, but it is rooted in questions that physicists working on the frontiers of string theory and cosmology are seriously exploring. In some models of eternal inflation, for example, new bubble universes are constantly being born in a chaotic, self-reproducing froth. These universes are not completely isolated. They arise from a shared, underlying dynamic quantum field, the inflaton field. If this field itself were to undergo a global phase transition, or if one of the bubbles were to decay in a particularly violent way, it is plausible that it could influence the adjacent regions of the inflating sea, potentially triggering a cascade of other bubble decays. It is like popping a single, large balloon in a room that is filled to the ceiling with other balloons. The shock wave from the first pop could be enough to cause the nearby ones to burst as well. The scenario becomes even more complex and more deeply interconnected when you add the possibility of quantum entanglement into the mix. Some speculative theories have proposed that different bubble universes may be, in some deep quantum sense, entangled with each other at the moment of their birth, sharing a deep, non-local connection through their shared initial quantum state. If one of these entangled universes were to undergo a radical and information-altering shift like a vacuum decay, it is not inconceivable that this could have a subtle or perhaps even catastrophic effect on the other universes to which it is entangled. This is more of a philosophical metaphor than a worked-out mathematical theory at this stage. But it highlights the profound and beautiful possibility that the different realities of the multiverse may not be as separate and isolated as we might think. Let us imagine what this multiversal domino effect would mean in practice. A universe, much like our own, tunnels into a lower energy vacuum state. Instantly, a bubble of true vacuum forms and begins to expand at the speed of light, erasing the old laws of physics in its wake. But as it tears through its own space-time, its expanding wall reaches the boundary of its own bubble universe. And it keeps going. It plows through the higher dimensional bulk space, its new, more stable vacuum state, overwhelming the fragile, false vacuum states of its neighboring universes, causing them to collapse as well. And each of these new collapses generates its own expanding bubble, and so on, and so on. One decay leads to another, and another, until entire chains, or even entire regions, of the multiverse fall like cosmic dominoes, tipping one by one in a silent, cataclysmic cascade. What is even more chilling is that, once again, we would never see it coming. If such a multiversal collapse were to start in a distant and completely unrelated chain of universes, there would be no signal, no warning, only the instantaneous rewriting of our own. Local physics the very moment the cascade reached our own cosmic neighborhood. Or perhaps, in a final, dizzying twist, we would not even notice. Some versions of this theory suggest that the collapse would not just erase our universe, but would erase all of reality, the entire multiverse, replacing it with something so fundamentally different that the very concepts of us and noticing would be rendered meaningless. Of course, all of this is deeply and profoundly speculative. We do not yet have any direct experimental evidence for the existence of other universes, let alone for the complex, and as yet unknown, mechanisms by which they might interact with one another. But the mathematics that describes the possibility of vacuum decay does not, on its own, provide a natural reason for it to be confined to a single universe. If the multiverse is real, and if its different realms are connected by a shared, underlying energy field or a common, higher dimensional fabric, then the threat of this ultimate quantum instability may be a universal one. In the most literal sense of the word, what this tells us is that the property of instability may not be an isolated, local feature of our own particular corner of the cosmos. The entire cosmic landscape, the whole of the multiverse, could be more like a fragile, intricate house of cards than a solid, eternal fortress of stone. Elegantly constructed, astonishing in its diversity, but ultimately and fundamentally delicate. One sudden, quantum shift in the vacuum, in any one of its infinite rooms, and the entire beautiful structure could begin to tumble in ways that we can barely begin to understand. In this sense, the multiverse is not just a grand stage for the playing out of countless independent stories. It may be a single, vast and interconnected system of interlinked fates. If one of the chapters of this cosmic book ends abruptly, it is possible that others may be forced to follow. And in the final, profound silence that remains, there will be no voice left in any reality to tell the tale. Imagine trying to detect the precise, instantaneous moment when the universe decides to delete itself. There would be no noise, no light, no final, dramatic warning. Just the sudden, complete, and silent redefinition of everything. This is the terrifying and beautiful signature of vacuum decay, an event so swift, so final, and so fundamental that it seems, on the face of it, to be utterly and completely undetectable. But for the scientists who are probing the very limits of physical reality, this silence is not an excuse for ignorance. It is a profound and fascinating challenge, a dare from the cosmos itself. Could we, with all our powerful instruments and our collective human genius, ever hope to see it coming? To even begin to answer this question, we must first understand what precisely it is that we are trying to measure. A vacuum decay is not an object, like a meteor on a collision course with Earth. It is a phase transition, a fundamental change in the state of space itself. Detecting it is not like spotting a distant galaxy. It is like trying to measure a change in the very fabric of reality, a moment before it unravels. This is a very different and far more difficult kind of problem. We are not looking for particles or for waves. We are looking for the subtle, telltale signs that the very rules that govern the behavior of those particles and waves are beginning to shift. But how could we possibly do that? One potential avenue of research involves making incredibly high-precision measurements of the fundamental constants of nature. If our universe is truly teetering on the brink of a transition to a new vacuum state, some theorists have speculated that there could be tiny, subtle anomalies, a kind of quantum leakage of information from the true vacuum that could manifest as a slight, and perhaps even time-dependent, variation in the values of these constants. For example, a tiny, almost imperceptible change in the strength of the electromagnetic force, or in the value of the fine structure constant, could be a hint that the vacuum is less stable than we thought. Physicists around the world have built incredibly sensitive devices, atomic clocks, laser interferometers, particle detectors that are capable of measuring these constants with a precision of 1 part in a billion, or even a trillion. But even this may not be enough. The problem, as we have seen, is that vacuum decay is not a gradual process. It does not broadcast its arrival. If it occurs, it does so via the instantaneous, probabilistic leap of quantum tunneling. The bubble of true vacuum simply pops into existence, somewhere, and begins to expand at the speed of light. There is no physical way to detect something that is moving towards you at the very same speed as the information that would warn you of its approach. If a vacuum bubble were to begin its deadly silent march on the far side of our own galaxy, we would have no knowledge of it until the very instant it reached us. And by then, of course, it would be too late. We, and our entire solar system, would already be inside the new vacuum, our atoms rewritten or erased, our familiar concepts of space, time, and existence rendered utterly meaningless. And yet, not all hope is lost. One of the more innovative and more promising approaches to this problem does not focus on the direct, real-time detection of a vacuum decay event, but on a more careful and more precise understanding of the risk. This is where the experimental frontiers of particle physics lie. At the Large Hadron Collider at CERN, scientists are not just smashing particles together to discover new ones. They are also, in a very real sense, probing the stability of the quantum vacuum itself. The Higgs field, as we have seen, is the quantum field that is most likely to be associated with the potential instability of our universe. And by creating and studying the properties of the Higgs boson with incredible precision, physicists can begin to map out the energy landscape of our cosmos. The discovery of the Higgs boson in 2012 and the subsequent precise measurement of its mass at around 125 GeV was the first crucial data point in this endeavor. And it was a deeply unsettling one. It placed our universe in the precarious, metastable zone. Not quite stable, not quite doomed. This is a chilling result, but it is also a powerful scientific foothold. If we can continue to measure the properties of the Higgs field and its interactions with other particles, like the top quark, with even greater precision, we might be able to calculate the odds of a vacuum decay more reliably. Some researchers are also pushing into the realm of pure theory, using our experimental data to map out what is called the vacuum stability phase diagram. This is a chart that shows the different possible fates of the universe based on the precise values of key parameters, like the mass of the top quark and the mass of the Higgs boson. If these parameters were to shift, even ever so slightly, the universe could be pushed from its current, metastable state into a region of absolute stability, or, more terrifyingly, into a region of catastrophic instability. With more and more precise, experimental data from future colliders, we might one day be able to refine this map and to say, with a greater degree of scientific confidence, we are safe or we are not. But even then, detection is not the same as prevention, and this is the most haunting truth of all. Let us say, hypothetically, that we developed a method to detect the spontaneous formation of a vacuum bubble in a nearby galaxy. What could we possibly do about it? If it is traveling towards us at the speed of light, we cannot outrun it. We cannot build a shield to block it. We cannot contain it like a chemical spill. The very laws of physics themselves would be rewritten in its wake. Preventing a vacuum decay is like trying to stop a mathematical equation from being solved. Once the process is initiated, the outcome is inevitable. That said, the boundless creativity of the human mind has, of course, led to some highly speculative, far-future theoretical proposals. These are more in the realm of thought experiments than of engineering plans, but they are a testament to our insatiable desire to find a way to control our own cosmic destiny. Some have suggested that a sufficiently advanced post-human civilization could learn to manipulate the quantum fields on a cosmic scale, perhaps by creating vast artificial energy fields that could reinforce our false vacuum, or that could steer a potential decay towards an empty, uninhabited region of the cosmos. Others have speculated that if we could precisely understand the quantum landscape of the multiverse, we might one day be able to find a way to tunnel our entire observable universe into a more stable vacuum state, a cosmic-scale engineering project of almost unimaginable proportions. And then there is the even more speculative and more philosophical realm of the simulated reality. Some physicists and philosophers, as we have seen, have entertained the idea that if we are living in a vast, sophisticated computer simulation, then a vacuum decay is not a problem of physics, but a problem of software. It could be a glitch in the code, or it could be a scheduled, and perhaps even periodic, system reset. In such a case, the detection of the event might come not from our physical sensors, but from our ability to recognize the subtle patterns, the code-level anomalies, the digital seams in the fabric of our simulated reality. This is a fringe idea, to be sure, but it underscores the sheer desperation and the boundless imagination of the scientific community when it is faced with a phenomenon that seems to defy all our traditional methods of detection and prevention. Despite all these challenges, the search continues. Every new high-energy experiment at the LHC, every new refinement in our quantum sensors, every slight, and as yet unexplained, anomaly in our astronomical data might hold a tiny, precious clue. Space observatories are now looking for unexplained, large-scale variations in the cosmic microwave background that might hint at other distant regions of space that are undergoing radical, phase transition-like shifts. Earth-bound laboratories are continuing to push the limits of precision measurement, hoping to catch the first, faint whisper of a cosmic instability before it becomes a deafening and final roar. And maybe that is the ultimate point. Even if we can never detect a vacuum decay directly, even if we can never prevent it, the pursuit itself is deeply and profoundly meaningful. In trying to detect the undetectable, we are forced to stretch our human ingenuity to its absolute limits. We refine our instruments. We unify our theories. We ask the most fundamental and most difficult of all questions: what kind of universe are we truly living in? And if the answer to that question is that we are living in a universe that is poised on a quantum razor's edge, a universe that is both beautiful and temporary, then knowing that truth, even without the possibility of escape, is a profound and noble triumph of understanding. Because sometimes, as we have seen again and again on this journey, it is only by chasing the invisible that we can truly begin to illuminate what is real. The story of our quest to understand the quantum world began not with a bang, but with a whisper, a series of strange and seemingly disconnected experimental results observed at the turn of the 20th century, a subtle but persistent hum of weirdness that the elegant clockwork universe of classical physics could not explain. There was the problem of black body radiation, the strange way that hot objects emit light. There was the photoelectric effect, the bizarre fact that light seems to behave not like a wave, but like a stream of discrete particles when it strikes a metal surface. The universe, it seemed, was not playing by Newton's rules. Into this state of growing confusion, stepped a generation of brilliant and often reluctant revolutionaries, men like Max Planck, who first proposed the idea of the quantum, a discrete packet of energy, as a desperate mathematical trick to make his equations work. And Albert Einstein, who in his miracle year of 1905 not only laid the foundations for his theory of relativity, but also took Planck's quantum idea seriously, using it to provide a brilliant and simple explanation for the photoelectric effect, an achievement that would eventually win him the Nobel Prize. But it was the Danish physicist Niels Bohr who, in 1913, took the first truly radical step into the new quantum reality. His model of the atom, with its strange and ad hoc rules about electrons jumping between discrete, quantized energy levels, was the first serious gesture towards a truth that would soon upend our entire understanding of nature. That reality, at its very core, is not continuous, but discrete, not certain, but probabilistic. Bohr's ideas were shocking and deeply unsettling at the time. They seemed to violate the most basic principles of classical physics. But they worked. They could explain the specific, discrete colors of light emitted by different atoms, a puzzle that had baffled scientists for decades. But the new quantum theory did not come without a deep and often bitter philosophical debate. The early pioneers of the quantum world were not a unified, happy band of revolutionaries. They were a group of brilliant and often fiercely individualistic thinkers who argued passionately about the very meaning of the strange, new reality they were uncovering. Einstein, despite having been one of the theory's founding fathers, could never bring himself to accept its most radical implications. His famous and often quoted line, "God does not play dice with the universe," was a direct and heartfelt rebuke to the inherent, irreducible randomness and probability that lay at the heart of the new quantum mechanics. For Einstein, a complete theory of nature had to be a deterministic one. Probability was a sign of our own ignorance, not a fundamental feature of reality itself. Bohr, the philosophical heart and soul of the quantum revolution, responded with his characteristic, gentle but firm, wisdom. Einstein, he is said to have calmly replied, "Stop telling God what to do." This philosophical battle, this deep disagreement about the very nature of reality, was not just a matter of rhetoric. It was a creative tension that would shape the course of physics for the next century. The quantum theory grew fast. In the 1920s, a new generation of young, brilliant physicists, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, developed the full mathematical formalism of quantum mechanics. Heisenberg's uncertainty principle, Schrödinger's wave equation, Dirac's relativistic quantum field theory, these were not just mathematical curiosities. They became the new and incredibly powerful scaffolding upon which all of modern physics would be built. With these new tools, scientists began to realize the full and often bizarre implications of the quantum world. They learned that particles could also be waves, and that waves could also be particles. They learned that reality itself could be smeared out in a superposition of multiple and often contradictory possibilities, until the very act of a measurement collapsed it into a single, definite state. Quantum mechanics was not just a new theory anymore. It was the theory, the most accurate, the most powerful, and the most successful description of the physical world that humanity had ever devised. By the mid-20th century, the strange quantum zoo of fundamental particles began to expand at a rapid rate. Physicists, using powerful new particle accelerators, discovered a host of new and exotic creatures, the muon, a heavy cousin of the electron, the neutrino, a ghostly particle that can pass through the entire Earth without interacting, the pion, a particle that helps to bind the nucleus of an atom together, the old, tidy picture of the atom as a miniature solar system, with a nucleus of protons and neutrons orbited by electrons, was replaced by a much more complex and much more vibrant reality. The protons and neutrons themselves were found to be made of even more fundamental particles, called quarks, which are held together by the strong nuclear force, carried by particles called gluons. Laboratories around the world, from Brookhaven in the United States to CERN in Europe, raced to catalog these new particles, to classify them, and to understand their strange and beautiful interactions. And from this ferment of discovery, a new and even grander dream began to emerge, the dream of a single, unified theory that could explain all of these disparate particles and forces within a single, elegant framework. This dream eventually evolved into what we now call the Standard Model of particle physics. The Standard Model is a stunning intellectual achievement. It is a quantum field theory that describes all the known fundamental particles and their interactions, with the exception of gravity. It successfully unifies the electromagnetic force and the weak nuclear force into a single electroweak force, and it provides a complete and remarkably accurate description of the strong nuclear force. The Standard Model worked almost too well. For decades, it correctly predicted the outcome of every single experiment that was performed in our particle accelerators, but there was one glaring and crucial absence. There was a ghost in the machine. The theory required the existence of a new particle, the Higgs boson, the particle associated with the Higgs field that is responsible for giving all the other particles their mass. Without the Higgs, the entire beautiful edifice of the Standard Model risked collapse. The search for the Higgs boson became the central, driving obsession of particle physics for a generation, and it led to the construction of the most complex and powerful machine ever built by human hands, the Large Hadron Collider, nestled in a 17-mile-long circular tunnel buried deep beneath the border between France and Switzerland. The LHC is a modern-day cathedral of science, a place where protons are accelerated to 99.9991% of the speed of light and then smashed together with an energy that recreates the conditions of the universe in the first, fiery moments after the Big Bang. Its singular and multi-billion-dollar goal was to find the Higgs, and in July of 2012, in a moment of high scientific drama that was broadcast live to a captivated global audience, scientists at CERN announced that they had done it. They had found the Higgs boson. It was the final, triumphant confirmation of the Standard Model, a testament to the remarkable power of human reason and collaboration to unravel the deepest secrets of the universe. But even in that moment of triumph, as the data was analyzed with ever greater precision, a new set of questions and a new set of anxieties began to emerge. The measured mass of the Higgs, as we have seen, was a suspicious one. It was a number that seemed to place our universe in a precarious and potentially unstable state. The human quest for understanding had turned a corner. For decades, we had thought that a deeper understanding of the quantum world would give us a greater sense of control, of mastery over the forces of nature. But now, as our knowledge has deepened, we are beginning to see that the very rules we have uncovered may point to our own potential, and perhaps even inevitable erasure. This is not to say that scientific progress has stalled. On the contrary, it has only accelerated. But the tone of the quest has changed. It has become humbler, more reflective, more aware of its own profound limitations. We are no longer just looking for new particles. We are looking for answers about our own fragile place in a vast and perhaps unstable cosmos. CERN continues to be at the forefront of this search. After the discovery of the Higgs, the LHC was upgraded and has been restarted at even higher collision energies. Scientists are now meticulously probing the properties of the Higgs field, searching for any sign of exotic decays, of hidden symmetries, of unexpected new particles that could hint at the new physics beyond the standard model that might be responsible for stabilizing our vacuum. The search for supersymmetry, for dark matter, for extra dimensions. Each of these theoretical ideas offers a potential path to a deeper understanding, but also opens up a new vista of profound and often unsettling questions. And the quest is not just happening at CERN. All around the globe, a new generation of quantum experiments is pushing the boundaries of our knowledge. At Fermilab in the United States, the Muon G2 experiment has recently delivered results that seem to show a small but persistent deviation from the predictions of the standard model, a tantalizing hint that there may be unknown forces or particles that are influencing the behavior of the muon at the quantum level. In Japan, vast underground neutrino observatories filled with thousands of tons of ultra-pure water are listening for the faintest, most ghostly whispers of the universe, the neutrinos that are produced in the heart of the sun and in distant, cataclysmic cosmic events. These ghost-like particles, which can change their flavor as they travel, may hold the key to understanding one of the deepest mysteries of all, why our universe is made of matter and not antimatter. And in laboratories from Canada to China, researchers are working with strange, new states of matter at temperatures just a fraction of a degree above absolute zero Bose-Einstein condensates, quantum lattices, entangled atomic clocks using these ultra-cold, highly controlled quantum systems to simulate the behavior of more complex and less accessible realities, from the interiors of neutron stars to the quantum foam of the early universe. Throughout all of this, from the chalkboard musings of Niels Bohr to the thunderous collision chambers of the LHC, a single golden thread binds every generation of quantum researchers, the insatiable and uniquely human need to know. We have cracked open the atom and found a vast, beautiful, and often terrifying cathedral of complexity. We have pushed our equations to their limits and found deep and seemingly irresolvable paradoxes. We have built machines that have allowed us to see the invisible, to touch the intangible, to measure the immeasurable. And now, as we stand at the very edge of what we know, we are faced with a truth that is both deeply humbling and profoundly beautiful. The more we learn, the less solid, the less certain, the less predictable our reality becomes. And yet, we continue to chase it. Not because we expect the universe to offer us any final, comforting reassurances, but because the search itself, the relentless, creative, and often courageous quest to understand, is what defines us. It is what makes us human. When the strange and beautiful laws of quantum mechanics begin to percolate from the arcane world of physics laboratories and into the wider culture, something remarkable happens. The cold, hard mathematics of the theory begins to melt, to transform, to acquire a new and more human meaning. The story of our universe, as told by quantum physics, is not just a scientific narrative. It has become a powerful and often profound cultural and philosophical one. It has begun to reshape the way we paint, the way we write, the way we dream. It is forcing us to ask, in new and more urgent ways, the oldest and most fundamental of all questions: what does it mean to exist? Quantum theory, by its very nature, is a theory of paradox. It tells us that the universe is not made of solid, definite certainties, but of shimmering, probabilistic waves of potential. It tells us that an object can be in many places at once, that a cat can be both alive and dead, that the very act of observation can change the nature of the reality being observed. These ideas, which were once the exclusive domain of a small community of theoretical physicists, have now infiltrated almost every facet of modern human creativity. Writers and artists have found in the quantum world a rich and fertile new landscape of metaphor. The Argentinian writer Jorge Luis Borges, in his fantastical labyrinthine stories, written decades before most people had even heard of the term, seemed to anticipate many of the core themes of the quantum worldview. His Garden of Forking Paths is a beautiful literary expression of the many worlds interpretation of quantum mechanics, a story of infinite, branching timelines. His Library of Babel is a vision of a universe that contains all possible information, a kind of cosmic wave function. Today's science fiction authors and screenwriters have embraced these quantum themes with a new and more explicit enthusiasm. Films like Everything Everywhere All at Once and television series like Dark have taken the bizarre, counterintuitive concepts of the multiverse, of collapsing realities, of nonlinear causality, and have used them to explore the deepest and most universal of human emotions: love, loss, regret, the search for meaning in a seemingly chaotic world. But the influence of the quantum worldview is not just limited to science fiction. The themes of uncertainty, of the shifting, fluid nature of identity, of meaning as something that is constructed in the act of reflection, these are ideas that have found a deep resonance in all forms of modern art and literature. But perhaps nowhere is the cultural echo of the quantum revolution more profound than in the realm of philosophy. For centuries, Western philosophy was dominated by a deterministic and often mechanistic worldview. The great debate was between the freedom of the human will and the seemingly inexorable clockwork logic of a universe governed by fixed and predictable laws. The rise of quantum theory has exploded this old dichotomy. It has shown us that the universe, at its most fundamental level, may not be deterministic at all. It has an element of intrinsic, irreducible randomness, of spontaneity, of creativity. Reality does not unfold like a pre-written script. It unfolds like a poem with many possible and often surprising rhymes and rhythms, a poem whose meaning is not fixed, but is created in the very act of its reading. This has given a new and powerful language to the insights of existentialist thought. If our universe is, as the physics of the Higgs boson suggests, perched precariously in a false vacuum, if it could, at any moment, spontaneously tunnel into a lower energy state and wipe out everything we know in a silent, light-speed flash, then we are left with a disturbing, but also deeply liberating, idea. Nothing is promised. There is no cosmic guarantee of permanence, no underlying, eternal law that ensures our survival. This is a thought that resonates deeply with the philosophies of thinkers like Albert Camus and Jean-Paul Sartre, who argued that in a fundamentally absurd and meaningless universe, our only freedom and our only responsibility is to create our own meaning, to live with an authentic and courageous rebellion against the void. For some, this realization is a source of terror. For others, it is a call to live more fully, more vividly, more presently. If the cosmos itself is uncertain, if our reality is a fleeting, fragile miracle, then every moment of clarity, every experience of beauty, every act of connection becomes infinitely more precious. In this sense, the theory of vacuum decay is not just a story about our potential doom. It is a story about the improbable and beautiful gift of our now. Each breath we take, each beat of our heart, exists only because the universe, in its infinite quantum lottery, has, for this moment, chosen to let it be. And that is a kind of poetry in motion. The quantum worldview has also begun to create new and fascinating bridges with some of the world's ancient spiritual traditions. This is not a matter of a simple and often facile proof of ancient wisdom by modern science. it is a more subtle and more interesting resonance, a recognition that these two, very different, ways of knowing may be pointing towards the same, deep, underlying truths about the nature of reality. The idea of a non-local universe, the fact that two entangled particles can be connected across vast cosmic distances, seems almost mystical in its implications. It evokes the ancient, spiritual notions of interconnectedness, of oneness, of the Indra's net of Buddhist philosophy, a cosmic web in which every jewel at every node reflects every other jewel. The Hindu concept of Maya, the idea that the visible, differentiated world of our everyday experience is a kind of beautiful and ultimately illusory veil that hides a deeper, more unified, and ultimately divine reality, finds a strange and powerful echo in the quantum idea that the classical world we see is just one, collapsed and partial, version of a much richer and more holistic quantum superposition. And the Buddhist teaching of impermanence, the understanding that everything is in a constant state of flux, that there is no solid, permanent ground beneath our feet, finds an eerie and beautiful resonance in the modern physical concept of quantum instability, of a universe that is a shimmering, flickering, and constantly evolving dance of probability and potential. For many, this convergence of modern physics and ancient wisdom has been a source of profound personal meaning, a way to foster a sense of humility and of awe in the face of a universe that is far stranger, more mysterious, and more beautiful than our classical minds can easily comprehend. The human response to the strange and beautiful truths of the quantum world is not just a scientific one, it is a deeply human one. We are not just atoms and waves, we are storytellers. We are meaning makers. And when we are faced with a universe that might, in a heartbeat, collapse into nothingness, a universe that is governed by the strange and paradoxical laws of quantum mechanics, we do not just run the simulations and calculate the probabilities. We write poems, we paint canvases, we compose symphonies, we ask the deep, and perhaps unanswerable, questions about who we are and why we are here. In this light, the human, cultural response to the quantum revolution is, in itself, a kind of quantum phenomenon, spontaneous, unpredictable, creative, and beautiful. The moment we began to probe the very fabric of reality, we began to unravel not just the equations of physics, but the very story of ourselves. We found that beneath the solid, classical layers of the world, there lies a pulsing, vibrant, and deeply poetic truth that reality is not a static thing, but a breathing, flickering, collapsing, and regenerating process. A process that is not unlike the creative unfolding of a work of art, or the beautiful, mysterious, and ultimately fragile arc of a human life. And so, as we stare into the quantum unknown, one thing becomes clear. We are not just passive observers of this cosmic drama. We are active and creative, participants in a dance that is both terrifying and transcendent. And that, perhaps, is the final and most powerful echo of all. In a world without guarantees, in a universe built on the shifting sands of probability, the most radical and most human of all acts is to create, not because it will last, but because, for a fleeting, beautiful, and miraculous moment, it exists. The universe is fragile. It is a delicate and beautiful structure, balanced on the sharp, quantum edge of uncertainty, a cosmic cliff from which it could, at any moment, tumble into an abyss of a new and utterly alien reality. Every second of our existence, every beat of our hearts, is a gift from a cosmos that pulses with the possibility of its own, instantaneous and silent erasure. The idea that the vacuum we inhabit could decay, that the very laws of physics that make our existence possible could crumble without warning, is a thought that is both profoundly exhilarating and deeply terrifying. But perhaps the most important and most human lesson we can learn from this ultimate cosmic fragility is the immense and irreplaceable value of the present moment. In the face of a universe that is so fundamentally tenuous, so beautifully temporary, what does it mean to truly and fully live? For all of our history, humanity's long and often difficult journey of exploration, both in the vast, external universe and in the deep, inner workings of our own minds, has been a quest to find a sense of meaning, a sense of purpose, in a cosmos that can often feel cold, vast, and indifferent. We have built great systems of thought, our religions, our philosophies, our sciences, to try and anchor ourselves, to find a solid ground of truth and certainty in a seemingly chaotic world. But what if the deepest truth of all is that there is no solid ground? What if the very foundation of our reality is not a rock, but a wave, a shimmering, probabilistic, and ultimately fleeting thing? The possibility that the vacuum of our universe could decay, that it could spontaneously tunnel into a new, more stable state, forces us to confront the profound and liberating possibility that we are living on a precipice, with no ultimate safety net beneath us. And this brings a radical and deeply clarifying shift in perspective. If everything is temporary, if everything could, in an instant, collapse, then perhaps the most meaningful and most rational thing we can do is to learn to live with courage and with grace, in the only moment we ever truly have, the now, the present moment, in all its fleeting and beautiful imperfection, becomes the only true certainty in an uncertain universe. The quantum world itself already challenges our classical, linear notion of time. The block universe view, which emerges from Einstein's theory of relativity, suggests that the past, the present, and the future may all exist simultaneously. A frozen, four-dimensional landscape through which our consciousness seems to travel. In this view, our powerful subjective feeling of the flow of time is a kind of illusion. In the same way, our deep-seated psychological attachment to permanence, our desire for a future that is a safe and predictable extension of the past, may also be an illusion. The present moment, the here and now, is all we ever truly have, and it is all we will ever have. The deep quantum fragility of the cosmos is a mirror that reflects back to us the deep existential fragility of our own individual lives. We are, each of us, living on the edge. Our existence is a temporary and beautiful flare in the vast, dark expanse of cosmic time, a fleeting arrangement of atoms that has, for a brief and miraculous moment, woken up and become aware of itself. From a broader cosmological perspective, the universe does not seem to care whether we live or die, whether we succeed or fail, whether we find love or are lost in solitude. But within the subjective and equally real scope of our own individual lives, these moments are all that matter. They matter precisely because they are all that we have. Our existence is a fragile and therefore precious gift. What then does it mean to live with this awareness? To know that we are not guaranteed anything, not our next breath, not our next love, not our next moment of success for some. This realization might lead to a sense of nihilism, of paralysis, of a feeling that if nothing is permanent, then nothing matters. But for others, for the existentialists and the mystics and the poets, it is precisely this awareness of our own and the universe's fragility that gives life its most profound and beautiful meaning. If we know that nothing is permanent, we are freed from the tyranny of the future, from the endless, anxious striving for a security that can never be truly achieved. We can learn to live more fully in the moment, to embrace our finite nature, to find joy not in the accumulation of things, but in the quality of our experience, to create our own meaning in a universe that does not provide one for us. To live on the edge, in this sense, is not to live in fear. It is to live with a heightened sense of aliveness, of presence, of gratitude. It is a call to reassess what truly matters to us. In the quantum world, as we have seen, nothing is fixed. Everything is fluid. Everything is in flux. And if we can learn to accept this as a deep existential truth, then we, too, can embrace this fluidity in our own lives. The things we think of as stable and solid, our jobs, our relationships, our very identities, are not as permanent as we often believe. And that is not a tragedy, it is an opportunity. It is in the uncertainty, in the unpredictability, in the spaces between our plans, that true creativity, true growth, and true beauty can arise. Take a moment, now, to think about how you are living your own life. Are you constantly planning for a future that may never come? Are you clinging to a past of memories and regrets that no longer serve you? Or are you here, right now, in this moment, the profound and unsettling? Fragility of the cosmos is a powerful invitation to return to the present, to be fully and consciously aware of each fleeting and irreplaceable moment. There is a deep and profound beauty in knowing that everything could end, because it makes the now infinitely more valuable. This knowledge does not rob us of our joy. It amplifies it. It makes every laugh, every hug, every sunset, every single human experience feel more vibrant, more real, more intense, because we understand, at a gut level, how precious and how temporary it all is. There is also something deeply and powerfully humbling in the realization that we live in a universe that could be destroyed by forces that are so far beyond our comprehension, let alone our control. The idea that a random quantum fluctuation could, at any second, wipe our entire reality from existence is a thought that forces us to confront our own profound insignificance in the grand cosmic scheme of things. But this should not lead us to a sense of despair. On the contrary, it should lead us to a sense of profound gratitude. When we are truly and deeply aware that everything can be undone in a moment, we are given the rare and precious opportunity to cherish what we have, to live with a greater sense of intention, to appreciate the simple, fleeting beauty of our own existence. In the grand cosmic ledger, nothing we do may be permanent. But that does not, in any way, diminish the importance of what we do. On the contrary, it makes every act of kindness, every moment of connection, every creative endeavor infinitely more meaningful. The awareness of our cosmic fragility also has a powerful ethical dimension. It prompts a rethinking of how we treat each other and how we treat our small and equally fragile planetary home. If the universe itself is so fundamentally uncertain, if our reality could disappear in the blink of a cosmic eye, then it becomes all the more important, all the more urgent, to be kind, to be compassionate, to build a world that is based on connection and on a shared sense of our own collective vulnerability. Life is short, yes, but it is also vast, and how we choose to spend our time, how we choose to relate to each other, is what defines the quality and the meaning of our existence. In a sense, the potential collapse of the quantum vacuum is not just a scientific concept, it is a powerful metaphor for our own personal experience of impermanence. We all face moments of uncertainty in our own lives, times when everything we know, everything we have built, seems to be on the very brink of collapse. But it is precisely in these moments of fragility, in these encounters with the void, that we find our greatest opportunities for growth, for transformation, for a new and more authentic way of being. The present moment, in all its fleeting and fragile glory, is where everything that truly matters happens. It is where we experience joy, where we experience pain, where we experience love, where we experience the full, rich, and beautiful spectrum of what it means to be human. And perhaps that is the greatest and most profound lesson that the strange and beautiful world of quantum theory can teach us, that the ultimate value of life is not to be found in its duration, but in its depth. And so, as we live our lives on the edge of this quantum precipice, let us not shrink from the uncertainty. Let us embrace it. Let us live fully and courageously in each and every moment, knowing that our time here is both exquisitely fragile and infinitely precious. We may be living on the edge, but that edge is where life truly happens. And in the final analysis, that may be the only certainty that is truly worth living for. As we have journeyed together through the strange, beautiful, and fragile fabric of our reality, as we have explored the deep, quantum uncertainties and the vast cosmic forces that govern our universe, one simple and yet profound truth stands out above all others. The present moment is the most precious, and perhaps the only thing we truly have. The universe may be poised on the brink of a catastrophic collapse. Reality itself may be a ticking time bomb, its fuse lit by the random, probabilistic nature of the quantum world. But in this very moment, right here, right now, we are alive. We exist. The sheer, overwhelming enormity of our universe, with its billions of galaxies, its vast, dark voids, and its mind-bending complexities, can often feel dwarfing, a source of existential anxiety. But it also offers us an incredible and almost miraculous gift, the chance to experience this single, fleeting, and unrepeatable moment in time. Every breath you take, every beat of your heart, is a small personal miracle, a temporary victory of order and complexity against the relentless cosmic tide of entropy. In the midst of the chaotic, quantum fluctuations of the void, in the deep and profound uncertainty of our cosmic fate, we, as conscious beings, hold within us the remarkable and unique ability to create our own meaning, to embrace the now, to live fully, deeply, and authentically. We cannot control the vast and often incomprehensible forces that shape our universe. We cannot, with any certainty, predict what tomorrow or the next moment may bring, but we can choose to live with a greater sense of intention. We can choose to appreciate the simple, profound beauty in the small, everyday moments that make up the rich tapestry of our existence. The quantum world may be fundamentally unpredictable, but that is precisely what makes each and every one of our experiences uniquely and irreplaceable, precious. So, take a deep breath, look around you, feel the sensation of the air on your skin, listen to the quiet, ambient sounds of your environment. This moment is yours, and it is a miracle. Embrace it, live it fully. In the face of a universe that is so fundamentally uncertain, let us find a deep and abiding peace in the knowledge that our time, however brief it may be, is our own to shape, our own to experience, our own to imbue with meaning. Let the profound and beautiful fragility of the cosmos inspire us to live with a greater sense of purpose, to cherish the now, and to find a deep and lasting beauty in every single passing second. The universe may be fragile, but we, in our conscious present moment awareness, have the power to make each and every one of our moments a small and yet magnificent miracle. Imagine a place where the foundational rules of the universe, the very laws of physics we thought were unbreakable, begin to crack under pressure. A world of quantum anomalies, where symmetries we hold to be sacred are unexpectedly broken, and the neat, predictable order of the classical world gives way to a reality that is far stranger, more subtle, and more profound. This is not a distant hypothetical realm. It is the very fabric of our own existence, a fabric that, when examined at its smallest scales, reveals a universe that is not just stranger than we imagine, but perhaps stranger than we can imagine. Today, we journey into this enigmatic world. We explore these mysterious breakdowns in symmetry, these glitches in the cosmic code that reveal the deep and beautiful gaps in our own knowledge and challenge our understanding of everything from the nature of matter and energy to the ultimate fate of the cosmos itself. At the heart of quantum mechanics lies a world that is fundamentally different from our everyday experience. It is a world of probability, of potential, of a reality that is not fixed until it is observed. This world is governed by a set of deep and elegant symmetries, principles that suggest that certain properties of a physical system should remain the same even as that system undergoes transformations in space, in time, or in its own internal configuration. These symmetries are not just beautiful mathematical abstractions. They are the source of the great conservation laws that form the bedrock of physics, the conservation of energy, of momentum, of electric charge. They are the source of the universe's order and predictability. But in the quantum realm, these symmetries are not always absolute. An anomaly is a situation where a symmetry that holds true in the classical world is unexpectedly and mysteriously broken by the subtle and powerful effects of quantum mechanics. These anomalies are not mistakes in our theories. They are profound and revealing features of nature itself. They are the places where our classical intuition fails, where the universe whispers to us that there is a deeper, more fundamental layer of reality that we have yet to fully comprehend. They are the cracks in the edifice of our current understanding, and it is through these cracks that the light of a new, more complete physics may one day shine. The standard model of particle physics, our current best theory of the fundamental particles and forces, is a triumph of 20th century science. But it is an incomplete triumph. It does not include gravity. It does not explain the existence of dark matter or dark energy. It does not tell us why the particles have the specific masses and charges that they do. Quantum anomalies are the signposts that point us towards the physics that lies beyond the standard model. They are the clues that will guide us in our quest for a more unified and comprehensive theory of everything. In this journey, we will explore some of the most fascinating and important of these quantum anomalies. We will begin with the quantum anomalous Hall effect, a strange and beautiful phenomenon where the quantum properties of a material can mimic the effects of a powerful magnetic field. Even in its complete absence, we will then delve into the world of chiral anomalies, which deal with the handedness of fundamental particles and reveal a deep and mysterious asymmetry in the laws of nature, an asymmetry that may be responsible for our very existence. We will explore the conformal anomaly, a breakdown in the symmetry of scale that has profound implications for our understanding of quantum gravity and the nature of space-time itself. And we will confront the gauge anomaly and the gravitational anomaly, deep mathematical puzzles that lie at the very heart of our attempts to build a consistent and unified theory of all the fundamental forces. Each of these anomalies is a window into a deeper reality, a glimpse of a universe that is more subtle, more interconnected, and more mysterious than we ever thought possible. They are not just problems to be solved. They are invitations to a new way of seeing, a new way of understanding, a new way of being in relationship with the strange and beautiful quantum cosmos we call home. The story of the quantum anomalous Hall effect is a beautiful illustration of how a deep theoretical concept in quantum mechanics can manifest as a real, measurable, and technologically relevant phenomenon. It is a story that begins not in the quantum realm, but in the classical world of 19th century physics. In 1879, the physicist Edwin Hall discovered that when an electric current flows through a conductor, and a magnetic field is applied perpendicular to the current. A small voltage appears across the conductor, in a direction perpendicular to both the current and the magnetic field. This Hall voltage is a direct consequence of the Lorentz force, the force that a magnetic field exerts on a moving charged particle. The magnetic field pushes the electrons in the current to one side of the conductor, creating a buildup of charge and a measurable voltage. The classical Hall effect is a simple, elegant, and incredibly useful phenomenon. It allows us to determine the sign and the density of the charge carriers in a material, and it is the principle behind many modern sensors and devices. A century later, in 1980, the physicist Klaus von Klitzing, working with a two-dimensional electron gas at extremely low temperatures and in the presence of a very strong magnetic field, discovered a quantum mechanical version of this effect. He found that the Hall conductance, the ratio of the current to the Hall voltage, was not a continuous quantity, but was quantized. It could only take on specific, discrete values, values that were precise integer multiples of a fundamental combination of physical constants, the square of the electron's charge divided by Planck's constant. This quantum Hall effect was a stunning discovery. It was the first time that a macroscopic, measurable quantity had been shown to be quantized with such incredible precision. It was a direct, macroscopic manifestation of the microscopic quantum nature of the electron's motion in a magnetic field. The strong magnetic field forces the electrons into a series of discrete, quantized Landau levels, and the perfect quantization of the Hall conductance is a consequence of the robust, topological nature of these quantum states. The discovery earned von Klitzing the Nobel Prize in Physics and opened up a new field of study, the field of topological states of matter. But the story does not end there. The quantum Hall effect, as beautiful as it is, requires the presence of a strong, external magnetic field. This is often inconvenient and limits its potential technological applications. But what if a material could be engineered to exhibit the quantum Hall effect without any external magnetic field? What if the material's own intrinsic properties could mimic the effect of a magnetic field? This is the essence of the quantum anomalous Hall effect. The anomalous here does not mean strange or unusual, but rather intrinsic or spontaneous. It is a quantum Hall effect that arises not from an external field, but from the material's own internal magnetic structure. The key ingredient for this phenomenon is the interplay between magnetism and topology. The materials that exhibit the quantum anomalous Hall effect are topological insulators, a new class of materials that have a very peculiar electronic structure. They are insulators in their bulk, meaning that electrons cannot flow through their interior, but their surfaces or edges are conducting. They have special, topologically protected electronic states that allow for the flow of current only along their boundaries. When such a topological insulator is made magnetic, for example, by doping it with a small amount of a magnetic element like chromium, something remarkable happens. The internal magnetization of the material acts on the electrons in the same way that an external magnetic field would. It breaks a fundamental symmetry of the system, time reversal symmetry. This symmetry states that the laws of physics should look the same if you were to run the movie of time backwards. A magnetic field, with its inherent directionality, breaks this symmetry. In a quantum anomalous Hall insulator, the intrinsic magnetization of the material breaks this symmetry, effectively creating an internal magnetic field that organizes the electrons into the same kind of quantized, edge-conducting states as in the standard quantum Hall effect. The result is a perfectly quantized Hall conductance, but with zero applied magnetic field. This is a profound and beautiful result. It shows how the abstract topological properties of a material's electronic structure can combine with the quantum mechanical property of electron spin to create a macroscopic quantum phenomenon. It is an example of emergence, where a complex collective behavior arises from the simple interactions of many individual components. The quantum anomalous Hall effect is not just a theoretical curiosity. It was first experimentally observed in 2013 in a thin film of a magnetic topological insulator. The experiments are incredibly challenging, as they require the precise fabrication of these exotic materials and measurements at extremely low temperatures. But the observation of a perfectly quantized Hall conductance at zero magnetic field was a stunning confirmation of the theoretical predictions. The discovery has ignited a new wave of research in condensed matter physics. Scientists are now searching for new materials that could exhibit the quantum anomalous Hall effect at higher, more practical temperatures. If such materials could be found, they could lead to a new generation of ultra-low-power electronic devices. The perfectly conducting edge states of a quantum anomalous Hall insulator are dissipationless. The electrons flow without any resistance, meaning no energy is lost as heat. This could be the basis for a new kind of topological electronics, with the potential for incredibly efficient and robust information processing. The quantum anomalous Hall effect is a beautiful example of how an anomaly, a breakdown of a classical symmetry, can be a source of new, rich, and technologically relevant physics. It is a story that connects the abstract beauty of topology, the strange rules of quantum mechanics, and the practical art of material science. A story that is still being written in laboratories around the world. The Chiral anomaly is another profound and subtle example of a classical symmetry that is broken by the effects of quantum mechanics. It is a phenomenon that lies at the very heart of our understanding of the fundamental particles and forces, and it has deep implications for everything from the structure of the Standard Model to the origin of matter in the universe. To understand the Chiral anomaly, we must first understand the concept of chirality. Chirality is a property of certain fundamental particles, like electrons and quarks, that is related to their handedness. Just as your left and right hands are mirror images of each other, but cannot be superimposed, these particles can exist in left-handed and right-handed versions. Chirality is closely related to a particle's spin, its intrinsic quantum mechanical angular momentum. For a massless particle, which travels at the speed of light, chirality is the same as its helicity, the projection of its spin onto its direction of motion. A left-handed particle spins like a left-handed corkscrew as it moves forward, while a right-handed particle spins like a right-handed one. In a classical field theory, if the underlying equations are symmetric with respect to left-handed and right-handed particles, then there should be a corresponding conservation law. The number of left-handed particles minus the number of right-handed particles, a quantity known as the axial charge, should be conserved in any interaction. This is the chiral symmetry of the classical theory. The chiral anomaly is the surprising discovery that this classical symmetry is broken at the quantum level. In certain quantum processes, the axial charge is not conserved. Left-handed particles can be turned into right-handed particles, and vice versa, in a way that violates the classical conservation law. This is not a failure of our theory. It is a deep and fundamental feature of the quantum world. The anomaly arises from the interaction of the chiral particles with the background gauge fields that mediate the fundamental forces. A gauge field, like the electromagnetic field, can be thought of as a kind of quantum ether that pervades all of space. And the quantum fluctuations of this field, the constant bubbling of virtual particles, can have a subtle and powerful effect on the chiral particles moving through it. One of the most intuitive ways to understand this is to consider the behavior of chiral particles in the presence of both an electric and a magnetic field that are parallel to each other. This configuration creates a kind of chiral pump. The magnetic field forces the charged chiral particles to move in circles into quantized Landau levels. The parallel electric field then acts on these particles, but it does so in a way that depends on their chirality. It can, for example, pump particles from a left-handed Landau level to a right-handed one, or vice versa, changing the net axial charge of the system. This process is a direct physical manifestation of the Chiral anomaly. The anomaly is not just a theoretical curiosity. It has profound and far-reaching consequences. In the standard model of particle physics, the weak nuclear force, which is responsible for radioactive decay, is a chiral theory. It treats left-handed and right-handed particles completely differently. In fact, the weak force only ever interacts with left-handed particles and right-handed antiparticles. This is a manifest violation of parity, or mirror image symmetry, a discovery that shocked the physics world in the 1950s. The consistency of the standard model as a quantum field theory depends on a delicate and miraculous cancellation of various chiral anomalies. The contributions to the anomaly from the quarks and the leptons in each of the 3 generations of particles must precisely cancel each other out. If they did not, the theory would be mathematically inconsistent and would give nonsensical, infinite answers. The fact that they do cancel is a powerful, albeit circumstantial, piece of evidence for the structure of the standard model, and it provides a deep and mysterious connection between the seemingly disparate worlds of quarks and leptons. The Chiral anomaly also plays a crucial role in our understanding of the strong nuclear force, the force that binds quarks together to form protons and neutrons. The theory of the strong force, quantum chromodynamics, has an approximate chiral symmetry that is broken by the anomaly. This anomaly is responsible for the decay of a neutral pion, a type of subatomic particle, into 2 photons. The observed rate of this decay is in perfect agreement with the prediction from the Chiral anomaly, providing one of the most precise and beautiful experimental confirmations of this subtle quantum effect. But perhaps the most profound implication of the Chiral anomaly is in the realm of cosmology. The universe we see today is made almost entirely of matter, with very little antimatter. This is a deep mystery. According to the standard Big Bang model, matter and antimatter should have been created in almost equal amounts in the early universe. As the universe cooled, they should have annihilated each other, leaving behind a universe filled only with a dilute sea of radiation. The fact that we are here, that matter exists at all, means that there must have been a slight asymmetry, a tiny excess of matter over antimatter. In the early universe, about 1 extra matter particle for every billion matter-antimatter pairs. The origin of this baryon asymmetry is one of the greatest unsolved problems in all of science. The Russian physicist Andrei Sakharov, in 1967, laid out the 3 necessary conditions for generating such an asymmetry. There must be processes that violate the conservation of baryon number. There must be a violation of C and CP symmetry, and there must be a departure from thermal equilibrium. The Chiral anomaly, in the context of the electroweak theory, provides a mechanism for violating baryon number conservation at the high temperatures of the early universe. This process, known as Phaleron transitions, could have been responsible for converting a primordial lepton asymmetry into the observed baryon asymmetry. While this is just one of several competing theories for the origin of matter, it is a beautiful example of how a subtle, microscopic quantum anomaly can have a profound, macroscopic impact on the very existence of our cosmos. The Chiral anomaly is a powerful and elegant reminder that the symmetries of our world are not always what they seem. It is a story of a classical beauty that is broken by the strange and wonderful logic of the quantum realm. A story of an asymmetry that may be the very reason we are here to tell the story at all. The conformal anomaly is another, and perhaps even more profound, example of a classical symmetry that is broken by the subtle effects of quantum mechanics. It is a breakdown in the symmetry of scale, and it has deep and far-reaching implications for our understanding of quantum field theory, of quantum gravity, and of the very nature of space-time itself. Conformal symmetry is a powerful and elegant extension of scale invariance. A theory is scale invariant if its physical laws look the same at all scales of distance and energy. If you were to zoom in or out on a scale invariant system, you would see the same physics at play. Conformal symmetry is even more restrictive. It requires that the laws of physics remain the same, not just under a uniform rescaling of all distances, but under any conformal transformation. A transformation that preserves angles but can stretch and squeeze distances in a non-uniform way. In a classical field theory, many of our most fundamental theories, like Maxwell's theory of electromagnetism, are conformally invariant, at least in the absence of massive particles. This symmetry implies a number of powerful and beautiful consequences, including the conservation of a specific type of current, the dilatation current. The conformal anomaly is the surprising discovery that this beautiful classical symmetry is almost always broken at the quantum level. When we try to define a quantum field theory, we run into a problem with infinities. The interactions of particles with the virtual particles of the quantum vacuum lead to calculations that give infinite answers for physical quantities like mass and charge. To deal with this, physicists have developed a powerful and sophisticated set of techniques known as renormalization. Renormalization is a way of absorbing the infinities into a redefinition of a few key parameters of the theory, like the bare mass and charge of the particles. It is a remarkably successful procedure, and it is the foundation upon which the entire standard model of particle physics is built. But it comes at a price. The process of renormalization inevitably introduces a new, arbitrary energy scale into the theory, a renormalization scale, and the physical properties of the theory, like the strength of its forces, are now found to depend on this energy scale. A force that is strong at high energies can become weak at low energies, and vice versa. This running of the coupling constants is a fundamental feature of the quantum world, and it is a direct violation of scale invariance. The theory is no longer the same at all scales. The classical conformal symmetry has been broken by the quantum effects that are tamed by renormalization. This is the conformal anomaly. One of the most important consequences of the conformal anomaly is its effect on the stress-energy tensor, the mathematical object that describes the density and flow of energy and momentum in a physical system. In a classical, conformally invariant theory, the trace of the stress-energy tensor is zero. This is a mathematical statement of the fact that the theory has no intrinsic scale. But when the theory is quantized, the conformal anomaly gives a non-zero value to the trace of the stress-energy tensor. This trace anomaly is a direct physical manifestation of the breakdown of scale invariance. It is a measure of how much the quantum vacuum itself contributes to the energy and pressure of the system. The conformal anomaly has profound implications across a wide range of physics. In the theory of the strong nuclear force, quantum chromodynamics, the conformal anomaly is responsible for a large fraction of the mass of the protons and neutrons that make up the atoms in our bodies. The underlying theory of quarks and gluons is nearly massless, and classically, it would be nearly conformally invariant. But the conformal anomaly gives a huge contribution to the trace of the stress-energy tensor, which, in a sense, generates the mass of the composite particles like protons and neutrons. Most of your own mass is not from the Higgs mechanism. It is a direct physical consequence of the conformal anomaly of QCD. It is the energy of the quantum vacuum, bound up inside the protons and neutrons of your body. In cosmology, the conformal anomaly plays a crucial role in our understanding of the early universe. The period of cosmic inflation is thought to have been driven by the energy of a quantum field in a nearly scale-invariant state. But the small deviations from perfect scale invariance, the small tilt in the spectrum of the primordial density fluctuations, are a direct consequence of the conformal anomaly. They are a measure of how the strength of the inflatons' interactions changed during the inflationary epoch. These tiny, anomalous deviations from perfect scale invariance are what gave rise to the seeds of all the structure in our universe. Without the conformal anomaly, the universe would have remained a perfectly smooth, homogeneous, and boring place. In the realm of theoretical physics, the conformal anomaly is a key concept in string theory. The consistency of string theory as a quantum theory of gravity depends on the cancellation of the conformal anomaly on the two-dimensional world sheet that the string traces out as it moves through space-time. This requirement of conformal invariance is an incredibly powerful constraint, and it is what determines the critical number of dimensions, 10, in the case of superstring theory in which the theory can consistently live. The conformal anomaly is, in a sense, the gatekeeper of string theory, the mathematical principle that ensures its consistency. And in condensed matter physics, the principles of conformal field theory, the study of quantum field theories that are conformally invariant, have become a powerful tool for describing the behavior of systems at a critical point. For example, a magnet at the precise temperature where it loses its magnetism. At these critical points, the system loses its intrinsic sense of scale, and its long-distance behavior is governed by the universal laws of a conformal field theory. The conformal anomaly is a subtle but profound concept. It is a story of a beautiful classical symmetry that is broken by the unavoidable and ultimately creative effects of the quantum world. It is a story that connects the mass of the protons in your body, the origin of the galaxies in the sky, and the very consistency of our most ambitious theories of fundamental reality. It is a reminder that the universe, at its deepest level, is a quantum universe. A universe where the simple, elegant symmetries of the classical world are often just a beautiful, but ultimately incomplete, approximation of a much richer, more subtle, and more dynamic reality. The gravitational anomaly is one of the most abstract, most subtle, and potentially most profound of all the quantum anomalies. It is a deep mathematical inconsistency that can arise when we try to combine the principles of quantum mechanics with Einstein's theory of general relativity, particularly in the presence of chiral fermions, the left-handed and right-handed particles that make up the matter in our universe. It is a puzzle that lies at the very heart of the quest for a theory of quantum gravity, and its resolution may hold the key to understanding some of the deepest secrets of the cosmos. To understand the gravitational anomaly, we must first appreciate the deep symmetries that underlie both quantum field theory and general relativity. The standard model of particle physics is built on the principle of gauge symmetry. This is a powerful, abstract symmetry that dictates the nature of the forces between particles. It requires that the laws of physics remain unchanged under a certain set of local, internal transformations of the quantum fields. The mathematical consistency of the theory, in particular the conservation of probability, depends crucially on this gauge symmetry being exact and unbroken. General relativity, on the other hand, is built on a different but equally powerful symmetry principle: diffeomorphism invariance, or general covariance. This is the principle that the laws of physics should be independent of the coordinate system we use to describe them. It is the mathematical embodiment of the principle of equivalence, the idea that gravity is not a force, but a manifestation of the curvature of space-time. The gravitational anomaly is a potential clash between these two fundamental symmetry principles. It can arise in a quantum field theory of chiral fermions coupled to gravity. The problem is that the quantum effects of the chiral fermions interacting with a curved gravitational background can sometimes conspire to break the gauge symmetry of the theory. This is a disaster. A theory with a gauge anomaly is mathematically inconsistent. It would predict probabilities that are not conserved, and it would give nonsensical, infinite answers. It is not a physically viable theory. For a long time, it was thought that the standard model of particle physics, with its specific and seemingly arbitrary collection of quarks and leptons, might suffer from such a gravitational anomaly. The theory contains chiral fermions, and it is coupled to gravity. It was a major theoretical worry. But in the 1980s, the physicists Luis Alvarez Gomez and Edward Witten performed a detailed and complex calculation and made a remarkable discovery. They found that, for the specific and peculiar collection of particles in the standard model, the potential contributions to the gravitational anomaly from all the different chiral fermions, the quarks and the leptons, miraculously and precisely cancel each other out. The standard model is, against all odds, free of any gravitational anomaly. This is a stunning and deeply mysterious result. It suggests a hidden and profound connection between the particle content of the universe and the consistency of quantum gravity. It is as if the universe knew that it had to have this specific and seemingly random collection of quarks and leptons in order to be a consistent quantum mechanical reality. The cancellation of the gravitational anomaly in the standard model is one of the strongest, albeit circumstantial, pieces of evidence we have for the deep, underlying unity of the fundamental laws of nature. It is a clue that the seemingly arbitrary structure of the standard model is not arbitrary at all, but is fixed by a deep requirement of quantum consistency. This principle of anomaly cancellation has become a powerful and guiding principle in the search for new physics beyond the standard model. Any new theory that seeks to extend the standard model, for example, by introducing new particles to explain dark matter, or new symmetries to unify the forces, must also be free of any gravitational or gauge anomalies. This is an incredibly powerful constraint, and it has been used to rule out a large number of otherwise plausible-looking theories. It is a kind of consistency check that any new theory must pass before it can even be considered a serious candidate for describing our universe. String theory, our most ambitious and well-developed candidate for a theory of quantum gravity, provides a beautiful and natural mechanism for anomaly cancellation. The theory, as we have seen, is only consistent in 10 space-time dimensions. And in this 10-dimensional space-time, the specific mathematical structure of the theory automatically ensures that all potential gravitational and gauge anomalies cancel out. This is one of the most remarkable and compelling features of the theory. It is as if the deep mathematical consistency of the theory itself dictates the particle content and the symmetries of the world, in a beautiful and profound realization of the bootstrap dream. The gravitational anomaly is a very abstract and technical subject, one that is far removed from the world of our everyday experience. But it is a subject of profound importance. It is a window into the deep mathematical structure of our universe. It is a story about the subtle and powerful ways in which the principles of quantum mechanics and general relativity constrain each other. And it is a story that has a beautiful and deeply satisfying, if still mysterious, ending. The universe we live in, with its specific and peculiar collection of fundamental particles, appears to be a universe that is exquisitely, and perhaps uniquely, designed to be free of the mathematical inconsistencies that would have made its own quantum existence impossible. It is a universe that is, in the deepest sense, self-consistent, the gravitational anomaly. And its miraculous cancellation in the standard model is a powerful whisper from the cosmos, a hint that beneath the apparent complexity and randomness of the world, there lies a deep, hidden, and beautiful mathematical order. The gauge anomaly, like the gravitational anomaly, is a subtle but crucial aspect of quantum field theory that deals with the consistency and integrity of the symmetries that govern the fundamental forces of nature. While the gravitational anomaly concerns the consistency of a theory when coupled to the external, classical field of gravity, the gauge anomaly concerns the internal, quantum consistency of the gauge symmetries themselves. As we have seen, the standard model of particle physics is a gauge theory, GE. This means that its structure is dictated by a principle of local gauge symmetry. This is the requirement that the laws of physics should remain the same even if we make different, independent transformations on the quantum fields at different points in space-time. To maintain this symmetry, the theory must include gauge fields, which give rise to the force-carrying particles, the gauge bosons, like the photon, the W and Z bosons, and the gluons. The gauge symmetry is not just an aesthetic principle, it is the very foundation of the theory's mathematical consistency. It is what guarantees the conservation of fundamental quantities like electric charge, and it is what ensures that the theory is renormalizable, meaning its predictions are free from the nonsensical. Infinite answers that can plague quantum field theory calculations. A gauge anomaly is a situation where this fundamental, classical gauge symmetry is broken by quantum effects. This is a much more serious problem than the breaking of a global symmetry, like the Chiral symmetry we discussed earlier. The breaking of a global symmetry can lead to interesting and observable physical phenomena, like the decay of the neutral pion. But the breaking of a local gauge symmetry is a sign that the theory is fundamentally inconsistent. It is a mathematical sickness, a sign that the theory is not a valid description of physical reality. The problem arises, once again, from the subtle effects of chiral fermions. In a gauge theory with chiral fermions, the quantum loop diagrams, which describe the interactions of the fermions with the virtual particles of the vacuum, can sometimes conspire to produce a result that is not gauge invariant. This would be a disaster. It would mean that the theory is not renormalizable, that it does not conserve charge, and that it is not a physically sensible theory. For the standard model to be a consistent theory of our universe, all of its potential gauge anomalies must cancel out. And, in another beautiful and mysterious miracle of mathematics, they do. The standard model has a very specific and intricate structure. It has a gauge symmetry group known as SU-X-SU-XU, and it has a very specific collection of chiral quarks and leptons arranged in 3, seemingly redundant, generations. When physicists calculate the potential contributions to the gauge anomalies from all of these different particles and forces, they find that, for each of the many possible anomalies, the contributions from the quarks and the leptons, with their specific and peculiar charges, cancel each other out with exquisite precision. For example, the contributions from the left-handed quarks in a given generation precisely cancel the contributions from the left-handed leptons. This is a highly non-trivial and deeply profound result. It suggests that the seemingly arbitrary structure of the standard model, the specific number of colors for quarks, the specific charges of the leptons, the existence of exactly 3 generations is not arbitrary at all. It is a structure that is tightly constrained, and perhaps uniquely determined by the requirement of quantum consistency, by the requirement that the theory be free of any mathematical sickness. This principle of anomaly cancellation has become a powerful and guiding principle in the search for physics beyond the standard model. Any proposed grand unified theory, which seeks to unify the strong, weak, and electromagnetic forces into a single, larger gauge group, must also be free of any gauge anomalies. This is an incredibly restrictive constraint, and it has been used to rule out many otherwise attractive-looking gut models. The fact that some of the most elegant and compelling gut models, like the one based on the gauge group SO, automatically and naturally satisfy these anomaly cancellation conditions is seen by many as a strong hint that they may be on the right track. The gauge anomaly, boy, then is a beautiful example of the deep and subtle interplay between symmetry, quantum mechanics, and mathematical consistency. It is a story of a potential fatal flaw in our theories that is miraculously and beautifully avoided by the specific and seemingly peculiar structure of the world we live in. It is a powerful piece of circumstantial evidence that the universe is not a random collection of particles and forces, but is a deep, coherent, and exquisitely self-consistent mathematical structure. It is a whisper from the cosmos that there is a deep and hidden reason for the way things are. A reason that is written not in the language of our everyday experience, but in the abstract, elegant, and powerful language of symmetry and quantum field theory. The gauge anomaly, in its absence, is one of the most profound and beautiful clues we have in our ongoing quest to read the mind of God. The whale anomaly, often used interchangeably with the conformal anomaly we've already explored, is a specific and crucial manifestation of the breakdown of scale symmetry in quantum field theory, particularly when the theory is formulated on a curved space-time background. While the conformal anomaly speaks generally about the breakdown of scale invariance, the whale anomaly specifically refers to the non-invariance of a theory under whale transformations, local position-dependent rescalings of the space-time metric. It's a subtle but important distinction that lies at the heart of our attempts to understand quantum gravity. In classical general relativity, the theory is diffeomorphism invariant, meaning the laws of physics are independent of our choice of coordinates. However, it is not, in general, whale invariant. A change in the local scale, a stretching or shrinking of our rulers and clocks that varies from point to point, would change the physics. But in a classical theory of massless particles, like Maxwell's theory of electromagnetism, the theory is whale invariant. The physics of massless particles does not depend on an absolute scale of distance. This beautiful classical symmetry, however, is broken at the quantum level. The quantum fluctuations of the vacuum, as we have seen, introduce a fundamental scale into the theory through the process of renormalization. This breakdown of classical whale symmetry in a quantum theory is the whale anomaly. The anomaly manifests itself as a specific, non-zero contribution to the trace of the stress-energy tensor, a contribution that is proportional to the curvature of the space-time background. It is a direct measure of how much the quantum vacuum responds to the geometry of the space it inhabits. This is a profound and beautiful result. It tells us that the quantum vacuum is not a passive, inert background. It is a dynamic, physical medium that can be polarized and energized by the very curvature of space-time. The whale anomaly has deep and far-reaching implications. In the context of the early universe, it plays a crucial role in the process of reheating after inflation. The rapid, exponential expansion of inflation dilutes all the pre-existing matter and radiation, leaving behind a cold, empty universe filled only with the energy of the inflaton field. As the inflaton field decays, its energy is converted into a hot plasma of standard model particles. The whale anomaly is a key part of this process. The changing curvature of space-time during the end of inflation can, through the whale anomaly, directly create particles from the quantum vacuum, a process known as gravitational particle production. It is a mechanism by which the energy of the expanding universe itself is converted into the matter and radiation that fills our cosmos. The whale anomaly is also a central and crucial concept in string theory. String theory, at its core, is a two-dimensional quantum field theory living on the worldsheet that the string sweeps out as it moves through space-time. The consistency of the theory, in particular the absence of unphysical, ghost states with negative probability, depends on this two-dimensional theory being conformally invariant, which means its whale anomaly must vanish. This is an incredibly powerful constraint. It turns out that the whale anomaly on the string worldsheet only vanishes if the background spacetime in which the string is moving satisfies Einstein's equations of general relativity, and if the number of spacetime dimensions is exactly 26 or 10. This is a truly remarkable result. It means that the dynamics of space-time, the laws of gravity, are not an input into string theory. They are an output. Einstein's general relativity emerges as a necessary condition for the quantum consistency of the theory. The requirement that the Weyl anomaly vanishes is what bootstraps the theory into a consistent theory of quantum gravity. It is one of the most beautiful and compelling arguments in favor of string theory, a hint that it is not just another quantum field theory, but a deep and perhaps unique framework for unifying all the fundamental principles of nature. The Weyl anomaly is a subtle, technical, and often overlooked aspect of quantum field theory, but it is a concept of profound beauty and power. It is a window into the deep, dynamic relationship between the quantum vacuum and the geometry of space-time. It is a key ingredient in our story of the early universe, and it is the central, organizing principle that ensures the mathematical consistency of our most ambitious and promising theory of quantum gravity. It is a beautiful example of how a broken symmetry, an anomaly, is not a flaw, but a source of deep physical insight, a clue that points us towards a richer, more unified and more beautiful understanding of the cosmos. The landscape of quantum anomalies, with its subtle and often counterintuitive breakdowns of classical symmetries, presents a profound and ongoing challenge to our understanding of the universe. It is a realm where our most cherished and fundamental principles, the conservation of charge, the symmetry of scale, the very consistency of our physical laws, are tested and found to be more fragile, more conditional, and more mysterious than we ever thought. From the dissipationless edge currents of the quantum anomalous Hall effect to the matter-creating potential of the Chiral anomaly, from the mass-generating power of the conformal anomaly to the consistency-enforcing constraints of the gauge and gravitational anomalies, we have seen that the universe, at its quantum core, is a place of deep and beautiful paradox. These anomalies are not imperfections in the cosmic design. They are the very source of its richness, its complexity, and its capacity for creative evolution. The universe we inhabit, a universe of stable matter, of distinct forces, of complex structures, of life itself, is a universe that is only possible because of these subtle and beautiful breakings of symmetry. A perfectly symmetric universe would be a perfectly boring universe, a sterile and featureless void. It is the anomalies, the glitches in the classical code, that allow for the emergence of the new, the unexpected, and the beautiful. The study of these anomalies has been, and will continue to be, a powerful engine of scientific progress. They have guided us in the construction of the standard model of particle physics, with its strange and beautiful pattern of anomaly cancellations. They are now guiding us in our search for a theory of everything, providing the crucial consistency checks that any new theory of quantum gravity must pass. And they are inspiring a new generation of technologies, from the dissipationless electronics of the topological age to the powerful transformative potential of quantum computing. But beyond their role in science and technology, the quantum anomalies offer us a deep philosophical and even spiritual lesson. They teach us a lesson in humility, a reminder that our classical, common-sense understanding of the world is a limited and provisional one, a useful approximation that breaks down in the face of a deeper, stranger, and more mysterious reality. They invite us to embrace the paradox, to hold the tension between the expected and the actual, between the symmetry and its breaking. They show us that the universe is not a static, finished, and perfectly predictable machine, but a dynamic, evolving, and endlessly creative process. A process that is constantly surprising us, challenging us, and inviting us into a deeper and more intimate relationship with its own unfolding mystery. The quantum world is not a world of solid facts, but a world of vibrant possibilities, a world where the very act of observation helps to shape the reality we perceive. And as we continue to probe this strange and beautiful realm, with our powerful new instruments and our ever more sophisticated theories, we are not just uncovering the secrets of the cosmos, we are also uncovering the secrets of ourselves. We are discovering that we are not separate from this quantum drama, but are an integral part of it. We are the observers whose gaze helps to collapse the wave function of the universe. We are the conscious beings whose existence is a testament to the beautiful and miraculous asymmetry of the cosmos. And as you lie on the threshold of sleep, as your own, classical consciousness begins to dissolve into the quantum, dreamlike sea of the unconscious. You can feel a sense of participation in this grand cosmic story. The anomalies of the universe are not just out there, in the world of particles and fields, they are also in here, in the deep, paradoxical, and endlessly creative mystery of our own human soul.